we can start the lecture today. So we are very pleased to invite Dr. Mal. And Dr. Mal graduated from India in 2017. Then he did some postdoc there. Then he moved to Taiwan. Now he's with Professor Liang Yongcheng, but he's now officially hired by the NCTS, okay, in Taipei. And today he's going to talk about this self-testing of quantum components. This is the introduction. So let's welcome Dr. Mal. Okay.
Thank you for the nice introduction and good morning. Welcome to everybody. So today, as you guessed from the title, that I am going to talking about some self-testing protocol and introduction. So from this introduction, you can easily guess that I am not going to talk about in details about some special particular work, but an overview of the subject, and it is not very at the high level. So it is mainly at the level of definition and at the level of some simple protocols, and in some cases I will go through some proof of some protocol, not in details but outline of some proof. So if you have any questions at any time, you can interrupt me and feel free to ask, not wait till to end, but whenever you can you have any question, just ask. So the plan of the talk is I will start with some motivation of this subject. Then I introduce the scenario of the self-testing, and next comes some examples of this self-testing and robustness analysis of the protocol, and also I will introduce some other scenario of self-testing and end with the summary. So at the current time, it is popularly called that it is the time of second revolution of quantum science and technology. It is hard to exaggerate the importance of this quantum technology in present era. So there are so many. To name a few, there are quantum sensing, quantum cryptography, quantum computing, genuine randomness generation. You have already heard about some of these. So these are very important quantum protocols, and for this technology one have to ensure that the underlying system is quantum. So this has quantum advantage over their classical counterparts. So for a particular quantum technology, that is quantum cryptography, which is mainly directly related to the self-testing protocol. So I want to motivate a little bit from this particular quantum information task, that is quantum cryptography, which actually secure the communication between receiver and sender. So to get a rough idea about this quantum cryptography, suppose there is a message and it is encoded. Can you guess what is the message? So if you have given enough time, I think some of you can guess what is the exact message here. So actually it is simple. There is a simple encoding. It is says that Sunday Alex will go to night market, and from the message you can see just I have shifted one alphabet to next. So just shifting the one alphabet, this message is encoded to this. So there is a key, that is the one shift of the every alphabet is the key. If anybody knows this key, they can decode the message. So this is the underlying idea of cryptography, that we can exchange message in a encoded version, and if you know the key, you can decode the message. But in classical system, in present day, which in classical communication system, whatever it is, telephone or mobile, messages are not completely secure. That means the third party can decode the message in principle. So the question is in quantum communication case, the situation is dramatically different, that you can secure your communication in principle, the third party cannot eavesdrop your message. So how it goes? So it is the famous BB84 protocol. This is two famous person, Bennett and Brassard. So here Alice is the sender of the message. So she encoded her message into some quantum system. You can think about this. It is a simple two-level system, a qubit. So here the plus and cross, this is a 2 sigma Pauli spin measurement. You can think about this as a sigma z basis, this is a sigma x basis. And this 0, 1, these are the two different eigenstates of sigma plus basis and cross basis. Alice prepared randomly states from this set of 4 states, and it is sent through some channel to Bob. And Bob will measure randomly on these 2 bases, plus basis or cross basis. So suppose Alice sent randomly some bits which is encoded into these 4 states, 4 non-orthogonal states, and after Bob measuring randomly, and from this there is a classical public channel. This channel is private, but this channel is public, means everybody can hear from the message what is exchanged through this channel. Now after after sending the encoded message from Alice's side to Bob's side, and after measuring Bob's on this particular basis, they reveal their choice of basis, not the outcome of the measurement. Bob will reveal in which basis he measured. If their basis matches, they keep the outcome. Suppose here Alice sends the plus eigenstate, and Bob also measures on plus basis. Their basis matches, therefore they keep the outcome. But here the basis is not matched, so they discard the outcome. After this protocol, at the end of this protocol, both of them has actually the same key. If this channel is ideal, and eavesdropper cannot touch the system, encoded system, in ideal case they will end with a perfect secure key by which they can communicate securely. But in reality, this channel can be noisy, and eavesdropper can get some information through the public channel. Now this version of the protocol can be also defined in the entanglement based scenario. To go going to telling about the entanglement based scenario, I just want to introduce briefly what is the entanglement. By definition, if the bipartite state is pure, then if the state is not of this product form, then the joint state shared between Alice and Bob is entangled. And in mixed case, the state cannot be written as a convex combination of 2 product states. So rho I, sigma I, these belong to Alice, this belongs to Bob. And operationally you can think of that this kind of state which are entangled, that means those states which cannot be written in this form cannot be created by local operation and classical communication. Local operation means Alice can act locally on her subsystem, and Bob can act on his subsystem, and they can communicate via some classical channel. So by this kind of operation, they cannot create some entangled state that are not in this form. So in entanglement is a very important significant resource with respect to many information processing tasks. To name a few, these are the famous protocol, dense coding, teleportation, secret sharing, distributed quantum computing. In all those cases, there are so many other examples also. The entangled state actually give some advantage over their classical counterparts. Now in entangled based scenario, here the this source sends the half of an entangled pair to Alice and half of an entangled pair to Bob. Now here Alice measures on her subsystem to create some state along at Bob's side. So here exactly, if the state is the maximally entangled state of this form, and if Alice measures in sigma x and sigma z, then C can create remotely the state of eigenstate of sigma x, sigma z here. And after that, again similarly, Bob will announce what in which basis he measured, and they will reconcile their basis, and if the basis matches, they will keep the outcome. The protocol is similar, but here the source is entangled and is coming from some unknown source. Now the problem is this: if this entangled source is used here for the purpose of cryptography to generate the secure key, now it may happen in cryptographic case the third party, actually the eavesdropper who supplies the entangled state, or the supplier have may have any connection with the eavesdropper, so they can manipulate the state source of the state, entangled state. If Alice and Bob bought some source from some supplier, then they have actually no knowledge on the source, whether it is actually entangled or not. So if this is the situation, what happened? Now see, you can see here the BB84 protocol actually provide the statistics when their basis will match, their outcome will be perfectly correlated. If they share maximally entangled state, suppose they measure sigma x Alice, sigma x also Bob, then always they will have same outcome. But if their basis does not match, their outcome will be completely uncorrelated. That means their basis does not match, the probability of getting plus or minus will be totally random. Now if you do not know the source, just know the measurement statistics. From the measurement statistics, if you do not know, this measurement statistic can be reproduced by another mechanism. So in this case here, the shared state is not entangled state. Here actually the mechanism is this, to reproduce the same statistics. Here actually the 4 qubit state, the actually first the 2 pair of 2 qubit state, first and third is possessed by Alice, and second and fourth is sent to Bob. And the first and second pair actually of this state, this is 0, 0 and 1, this is the eigenstate of sigma z basis. Then the first and second, this pair is this is a separable state, and third and fourth pair is this state. And here 0 and 1 means these are the up state of sigma x basis and down state of sigma x basis. Now the protocol is, suppose Alice choose to measure in sigma z basis, then she will measure on the first qubit, and if Bob also choose to measure in sigma z basis, he will measure on second particle. But on the other case, when they choose to measure sigma x, Alice will measure on third qubit and Bob will measure on fourth qubit. You can see easily by some straightforward calculation that this protocol can exactly reproduce these statistics. Then what does it mean? This means that even they do not share a perfectly maximally entangled state, if the same statistics BB84 protocol can be generated in this scheme. But this protocol is not secure, because as this is separable, it has some purification which may be possessed by some eavesdropper. As this is a reduced state is always separable of an entangled state. So as this is the separable state, it have a purification which can be possessed by the eavesdropper. Now when Alice and Bob want to generate some secure key by measuring in this way on this state, this information can be also accessed by the eavesdropper. Therefore this way of generating key is not secure. So it is not secure because we do not know, they do not know what is the source actually. If they know that the source is maximally entangled state, it is secure. But if they do not know what is the source, they only know the statistics. The same statistics may have come from some separable, sharing some separable state which is not secure. Now this is the motivation for historically when self-testing was introduced. So historically, the self-testing was introduced by here is a, in a nutshell, self-testing means we have to gain some knowledge about the underlying state or underlying quantum feature of the state, whether it is working in a quantum mode or not, only looking at the observed statistics in addition with some minimal assumptions. So what are the assumptions here I will come to later, but the main point is this: only at the level of observed statistics, looking at the observed statistics, we have to provide some certificate whether the underlying system, what is the nature of the underlying system. So therefore it is called self-testing quantum components. So here this is the paper where originally it was introduced. The name self-testing was also given in this paper by Myers and Yot in 2004. So the problem they want to address, suppose you have a reference experiment and actual physical experiment means actual experiment which we do in laboratory. And reference experiment means the ideal setup, ideal state and ideal measurement. If two probability matches, that means you observe the same probability for both scenario, physical experiment and the reference experiment matches with the probability. Then there exists some isometry, means what is isometry, I will come to this point. So this means there may be some mapping between the reference state, underlying state and measurements, and the physical and state and measurement if their probability matches. This will not happen in general, because if this happen, then we call that we can self-test this reference state and measurement. That means actually in physical experiment we have those states. This is actually related by some local transformation to the actual state and measurements. Because you can look to appreciate why if probability matches, the underlying state and measurements may be different. Here you can see that in quantum theory, any joint probability can be reproduced by Born rule. The rho is the joint state, this A is the measurement done by Alice, and B is the measurement done by Bob, small b is the outcome, given that Y is measurement choice. So this actually mapping is one to many. That means you can have also a different state and different measurement which can reproduce the same statistics. So in the state space, this is the state space form a convex cone, and also set of measurements from a convex cone. You can think of that this blue state and blue measurement is the first settings, and the red state here and red state measurement is the second settings. But both reproduce the same statistics. So therefore this mapping is one to many. So if you told the statistics, you cannot identify what states and measurement actually is in the device. So this is the problem. This problem actually self-testing want to address. Now existence of self-testing means here in mathematically the existence of an inverse map. That means given the probability, can I identify in some particular state and measurement? So the take-home message is this from there: it is not possible to infer exactly the reference state and measurement, because as I said just previous slide, some extreme points of the set of quantum correlation allow unique realization up to some local transformations. These local transformations, what are those exactly, I just come to later. This was also mentioned in this work by this group also in our institute, university professor, one of the professor. So they also shows that there are some extreme point of the set of quantum correlation for which this inverse mapping can be found. So that means self-test can be possible for some extreme points of quantum correlation. In self-testing, one aims to infer the form of the state and the measurement from knowledge of the correlation only. That is in a device-independent scenario. This is actually the premise of the device-independent quantum technology. So just briefly to introduce again what is the device-independent scenario. It is the scenario of Bell test. So what is Bell test? So you can look here that Here from the source some entangled particle goes to one side and another side. You can think about this Alice and Bob. But in device independent scenario, we do not trust on the system that the source or device. That is, they are completely black means we do not know, we only know the input and output. But how the input and output are related, that means given an input, how the output is generated. What is the source? What is it a qubit or qubit, or it is a neutron or proton or electron? We have no knowledge about these things. Just we know that we have some settings, we can change the settings, that is the input, and given the settings we can have some output. So only we can have the probability of this output given some input. This is a black box scenario, and this is in this scenario. In this scenario, if the correlation, that is a joint probability distribution, can be generated in such a way where lambda is some shared randomness, the variable carrying with the particle here, which come to here and here. Suppose this particle carrying some another variable called lambda, or set of variable, whatever it may be, we call it lambda. Depending upon this value of the lambda and input, here I have a mistake. Here it should depend also upon lambda. The probability of A will depend upon x and lambda, and probability of B will also I and lambda. If their joint probability can be written in a factored form at the lambda level, then statistics can be actually simulated by some classical way, or if sharing some separable state, these statistics can be always simulated. But if they share some entangled state, or if the joint probability cannot be written in this form, though it is shown, it is called that the correlation is non-local. That means by some local model the correlation cannot be reproduced. So this is actually captured by some inequality which is known as Bell inequality, which is a linear function of the probabilities, and if this correlation is created by some shared randomness, it have a bound which is called local bound. But quantum theory can violate this. That means quantum theory exhibits non-locality. So here you can see that this is the region where these points actually are local point, and quantum set actually is a larger set. In any line of this form, actually a Bell inequality. Any line which can separate the local region from quantum region represents the Bell inequality. And this point, quantum point, is a quantum realization. If there is some state and measurement, if any point can be realized by some quantum state and measurement, we call it a quantum correlation. And in the 2-2-2 scenario, that means simplest Bell scenario, is the captured by the CHSH inequality, where Alice have 2 binary measurements and Bob have also 2 binary measurements. In this scenario, the CHSH inequality is bounded by 2 when they shared some local correlation. And this is the correlation, how it is defined. And quantum theory violate up to maximally 2√2. Now in this setting, to self-test underlying system and measurement, there are some basic assumptions. They also, if we self-test on the basis of Bell inequality, then there are some these assumptions, actually the assumptions of the Loophole free Bell test. The first assumption is the validity of quantum theory. That means the probability will be generated by some quantum states and measurement. Here we only consider about quantum non-locality. If non-local non-local data is produced, we know that it can be produced by some quantum states and measurement. And the second assumption is this: Alice or Bob are spatially separated region, and when they measuring, they do not have any communication. And choice of inputs is totally random. That means they are free to choose their input, what they want to measure. It will be not determined by some variable which also determine the source. And the last point is that always we will assume that the source are IID. That means every time the same state is sent by the source. So with this assumption, now the settings of the problem is here. whenever they shared some mixed state, we can have always some purification which is not possessed by them. The reduced state looks like a mixed state, but always it can have some purification. So these statistics can be generated by the measurement on Alice, measurement on Bob, but the trivial measurement of the purification part. That means nothing, doing nothing on the purification part. So this pure state, which is a tripartite state, if this measurement generates statistics from rho AB, also these statistics can be generated from this tripartite state where the third party measurement is a trivial measurement. That means nothing is done here. Now, due to the unitary, these statistics you can put here some unitary operator here. You can see from here this kind of measurements that are rotated by some unitary u, and this measurement is rotated by unitary v. And this state, the unitary u cross v rotated state, this state also generate the same statistics. So there is this is the another one notion of ambiguity, and another notion here that one cannot rule out the additional degree of freedom. There may be some additional degree of freedom on which the trivial measurement is done. This kind of operation you cannot rule out. So these actually suggest what kind of isometry or what kind of local transformation we have to consider here. So whenever we say that two probability matches, what is the underlying state? Those underlying state is actually equivalent up to some isometry. So this is the form of isometry. So this isometry means this is a unitary operation, but here the input state and output state dimension may not be equal. Therefore, it is not it is isometric operation. That means a dimension of output state can be greater than the dimension of the input state, but inner product will be preserved. The isometry is an operation which preserves the inner product but not the dimension of the Hilbert space, as you have the choice to take some extra degree of freedom. So local isometry means Alice, on Alice's side the Alice have also have the same operation kind of, and on Bob's and Bob's side, on Bob's side, Bob can take also extra degree of freedom on which they can act some unitary jointly. So after this operation, if they can extract the state to the ancilla states, that means if this joint operation, that is local isometry, which is operated in this way, if with this operation, if they can extract the target state, that is the reference state, to the ancilla qubit, then actually it is the signature of self-testing. That means the self-testing means the existence of this kind of isometry, where on the physical state, if we can find mathematically that this kind of mapping exists, so that we can extract the reference state here, that is the ancilla state, output ancilla state, then we can say actually the physical system actually has this test previously also. If this kind of isometry does not exist, we say that in the physical system may not have this kind of states. So here actually what I just mentioned here previously. So now the exact definition here comes, that we can, this is a reference state and this is a physical state, and if they are compatible with the same statistics, then we can say that there is always exists some purification, where also the state and the measurement can be self-tested if the measurement also done on the reference state. If this after operating local isometry on this state, we can have the measurement actually done on the reference state, but there are other degrees of freedom which is actually useless. So we call it the junk state. That means that only the measurement actually acted on the reference state to reproduce the statistics, but other degrees of freedom actually remains untouched, or in this scenario remains useless to reproduce the statistics. So now, it is to be noted that it is not necessary that one actually perform the isometry in the laboratory. In the laboratory, you will measure on the system in a natural way, but this is actually the mathematical proof whether we can have a self-testing or not. Now I will give some simple example where you can find the example of this protocol. So this is a example of one example of isometry where this is actually a partial swap gate. This local isometry is implemented by some partial swap gate at Alice's site, and this gate actually implements some partial swap operation on Bob's site. This operation actually extracts the physical state to the output ancilla state. This is the extraction map. And this is the Myers and Yo's original example. If the statistics satisfy these conditions, these are the measurements, 2 measurements done by Alice and 3 measurements done by Bob. If they observe that their measurement statistics has this, observe that the measurement outcome has this probability, then they can always construct. I will not go into the proof, that the statement of the self-testing problem is this. If this statistics is satisfied, they can always construct some local isometric mapping so that this condition is satisfied. That means if this probability is observed, the underlying state is actually maximally 2-qubit entangled state, or isometrically equivalent to maximally 2-qubit entangled state, and measurement are the sigma. These are the sigma x and sigma g measurement. Now I go to the self-testing in the Bell test scenario. So actually before this, the Myers-Yor protocol, long back to 1992, Popescu and Rodluck also asked the question which states actually violate the maximal Bell inequality. They consider CHSH inequality. Actually this has actually the spirit of same as the spirit of self-testing also, because they identified a class of states which violates CHSH Bell inequality maximally. That means 2√2, and this is a unique class of state where these are the higher dimensional state, but they have 2×2 subspace, where in this subspace they have the maximally 2-qubit entangled state. These are equivalent to, in this 2×2 subspace is a maximally entangled state, also maximally entangled state if the state in n dimension can be written in this form, that is the direct sum of 2×2 subspace. In every subspace there is maximally entangled state. So if one can observe the maximal violation, then state have to be of this form. This also noticed in 1992. So later actually it is noted that self-testing based on Bell inequality actually is the spirit of the Popescu-Rodluck's questions. So here the central question is to prove will be to show that Alice and Bob's local observable are anti-commuting, and from this anti-commuting structure they will construct the local isometry. If they can construct the local isometry, then it is proved that that point can be self-tested. So here is a simple example of this thing, that the SOS means sum of square decomposition. Every Bell inequality can be written in term of some square term, therefore this name is sum of square decomposition. So here is the maximal violation times identity operator and minus the Bell operator. This is a positive definite operator, therefore it has this SOS decomposition. From this decomposition, one can easily found that if the Bell expression is maximally violated, that means if its value is 2√2, that means it is 0. From this one can extract the condition of between the operator, and from this one can construct the isometry. Here the isometry network, the ZX operator can be constructed in terms of the measurement done by Alice and Bob. So by this construction, this Z and X is actually anti-commuting by this construction, and this was 0, this was already previously it was noticed that this anti-commutator on the support of psi is 0, and by construction this is also anti-commutator. Now this on the circuit, if one put this ZX in terms of A and B, and it is again a straightforward calculation one can find after applying the local isometry, the joint state has of this form, and this is actually simplifies to this form where the target state can be product with everything other state. That means one can extract the maximally entangled state from the physical state applying the isometry which is defined. And also here this isometry can be operated on the level of operator. This means A not acting on psi, this if one apply this isometry, one can find that this is actually measuring some Pauli operator on the maximally entangled state, and rest of the thing is just remains product. Now I next move to the robustness of the protocol. To be practically viable, the protocol have to allow some error. That means ideally we cannot have some maximal violation exactly to root 2. We have always some less amount of violation. So, or we observe some approximate statistics, not the exact statistics. So this kind of error always remains in the laboratory. So if our protocol have to be practically viable, then experimental error, this is inevitable, and the another error maybe come from the finite statistics. Finite, because we always calculate probability from finite data. So how to address this question? Also in this paper they also address how to address finite data sample, but I here want to also mention only the first case when we have some error in the apparatus, measuring apparatus. So in this case the robustness self-testing statement is this: if we observe some approximately close to maximal violation, our self-testing statement will be give some lower bound on the fidelity. That means we have the state close to the maximally entangled state. If we want to get some violation to root 2 minus epsilon, then we have to be able to say that our actually the original state is close to the maximally entangled state by some function of epsilon. This is the notion of robustness of self-testing. So far, the most robustness criteria is derived by these people in this work, which is based on operator inequality. This technique actually gives the most robust self-testing protocol so far we know. So here actually the notion is to find out some operator inequality of this form, where B is the Bell operator, S and mu some real number, and K is again some operator. So one have to construct some operator inequality of this form. So here the lambda is the local channel that is related to local isometry. One can extract the state, reference state from the physical state. This K actually of this form. Now if one can take the trace of this operator with respect to rho, that means one find the expectation of both side, right and left, and this gives the function. This is the actually desired fidelity measure. That if we have for some lambda, this fidelity will be greater than this right hand side, but that means we have to find here S and mu. If we can find S and mu, then we have the lower bound on the fidelity. And it is actually calculated that considering the lambda as a dephasing channel, it will be not give the optimal lower bound, but is a suboptimal lower bound. Considering the dephasing channel as the extraction channel, analytically they actually here found what is the value of S and mu. So it is the example of robust self-testing. Now I move to the other scenario. Finally, there in outside the Bell scenario, which is device independent, there are also semi-device independent scenario. What does it mean by semi-device independence? That means we do not have full trust, but we have some additional assumption. The advantage of this here, additional assumption can overcome some of the mathematical difficulty which appears in device independent scenario. And another, the experimental setup may be such that we have to know option to resort into the semi-device independent scenario. That means level of trust is such that we cannot have device independent scenario. So here there are 4 examples of the semi-device independent scenario. One is based on steering, where it is called one-sided device independent scenario, prepare and measure scenario, contextuality based protocol, and the protocol based on Leggett's inequality. So I just mentioned this very briefly. The steering based scenario here, the Bob is trusted, that means it is quantum, and this is the Alice which is measures in a black box, on a black box. So here actually basic object of study is the assemblage which Alice can create on the Bob side by measuring on her subsystem. So these assemblages are the basic object of study here. The local hidden state model actually here, actually the local model, if the Bob assemblage at Bob side can have some local hidden state model, then it is not steerable. Or if this Bob side's assemblage have not such kind of local hidden state model, then it is steerable. So now in this setting, in the recent work also here by Professor Yen and Chen group, also I find that in a recent work they show somehow that in this scenario, say they have some device independent statement. Although the scenario is one-sided device independent, but they have some device independent statement here. For 2 applications here, in one application they use this protocol to self-testing the steerable assemblage, the certification of entangled 2-qubit state which is proposed in this paper, and another application it can be used to verify the non-entanglement breaking channel with fewer assumptions compared to the some work which is previously done. So this is interesting. Next interesting is the self-setting is the prepare and measure scenario. Here X is the preparation device, measures some state and send to Bob who will measure. So it is preparation device and it is measurement device. Here the basic objective study is this. On the prepared state, Bob is measured this. So here is the outcome of Bob, given that Alice has prepared this state and Bob has measured this. So in this scenario, it is interesting that in the previous scenario, always the self-tested measurement or the projective measurement. But in this scenario, POVM, which is the most general quantum measurement, can be self-tested also. And the final measurement, I will just go through briefly here. The self-testing of measurement in the Leggett's scenario, here we also introduce this thing in the semi-device independent scenario. So it is the Leggett's scenario here. Is the scenario some input state Alice is measured and some earlier time, and again later time Bob will measure, and with their measurement outcome they have temporal correlation. That means the correlation which comes from 2 different time measurements. So with this correlation again one can have some inequality which is called Leggett's inequality. This actually comes from some assumption. The original assumption was reality, notion of macro realism, but here in our purpose to self-test, we can have some different assumptions also. From the different assumption, we also can derive the Leggett's inequality. So here the predictability means the observed probability will be always 0 and 1. That means the event can be predictable. And no signaling in time means the first measurement cannot influence the second measurement statistics. So with this operational assumption, one can derive the inequality, it is called Leggett's inequality, which is bounded by 2 means if these 2 assumption is satisfied, it cannot be greater than 2. If it is greater than 2, that means violation of Leggett's inequality. Now with this assumption, the input state is quantum, and on the Bob will always measured on the post measurement state of Alice. With this assumption, here we can self-test what is the actually measurement of Alice and Bob. If the Leggett's inequality is varied maximally, that means 2 root 2 if we found, then the Alice's measurement, Alice has 2 measurement choice, they must have to be either sigma g, sigma x, and Bob 2 measurement have to be this form or unitary equivalent to this. It is the qubit example. But we can have higher dimensional example also using the Jordan lemma. We can have always 2 by 2 block diagonal form of the higher dimensional measurement if we have 2 binary measurement. Then also this allow to construct such form of isometry, and I just skip there. We also, for higher dimensional case, we also allow this isometry to self-test the form measurement. And again, here we also have the robustness. That means is this practically viable. We can also test Legge-Gard inequality to self-test this form of measurements. And finally, I conclude with summary that so far what I said, we have the take-home message that motivating self-test from the perspective of security of QKD, then define the premise of self-testing together with the pertinent notion of equivalence, that is local isometry, then self-testing singlet and anti-commuting qubit measurements based on Bell theorem and without Bell theorem. Without Bell theorem is the original Myers-Yos protocol, and self-testing in steering and prepare and measure scenario, and finally certifying 2 outcome measurements employing violation of Legge-Gard inequality with some robustness. Thank you for your attention.
Thank you very much for a nice talk. Now it's time for comment and question. Do you have a question?
It seems quite against the notion of the local isometry, but you mentioned the isometry usually is not one-to-one. So you have you can find some kind of reduction state B. And is there any more physical content or physical condition of this state? Because if you treatment, you only focus on the first part. So you have A, B, and then A prime, B prime. You want to fit this part, but the price of local isometry is the net. Usually you will have another C part here. And is there any other physical information of what physical content in that part?
Yes. Yes. So here it can be seen that now the concern is this: at the local isometry here applied LHS side and local isometry here applied box side. After applying the local isometry, this is the target state, this is the jump state, and this measurement is done. Then after local applying isometry, the actual statistics actually coming from this part. Here the structure is this the everything is in product form with this reference state. Therefore the physical information which we have, that means the statistics. So all of the information actually encoded in this side as it is in the product form. So we have the physical information here, only the observation. We have no other physical information. All that physical information actually on this side here. This jump state has no information about the object. It can have other information, but we do not observe that information. So our observation of statistical information always remains in this side, not in this. It is the actually the motivation of introducing the color. So we want to infer from the observation. So we do not, what we do not observe, that information we do not share.
So it's very nice to see you have generalized this self-testing to this Legge-Gard inequality. So my question is that have you ever thought about to put this on the IDF constant device?
Oh.
To do self-testing on this? No, you haven't thought about it. Okay. So the second question is that so in this Legge-Gard inequality, so you have assumed this no signaling in time condition. So my question is that if you relax a little bit, if you allow somehow a little bit this signaling in time, but not too much. So does your theorem still hold? If you allow a little bit, not too much signaling effect.
So here no signaling assumption we use to derive the Legge-Cut inequality. So if I allow some amount of signaling, then Legge-Cut inequality which we derive in this way we cannot derive.
You cannot. Okay. Okay. So this.
To derive Legge-Cut inequality, we have to satisfy no signaling.
Yeah. Yeah. Okay. So by the way, do you miss any comment? Because people talk about this scenario, they will call this temporal CHSH, not the Legge-Cut inequality. Yeah, right. Because Legge-Cut inequality is testing is a macro-realism. Yeah, but actually, what you have done is temporal CHSH, right? Okay.
Yes.
Yeah.
Here, actually, I called it Legge-Cut temporal CHSH inequality Legge-Cut because the different measurement done by Bob actually can be seen from in Schrodinger picture. The state is evolving, the measurement is same.
Yeah.
So
Okay.
as those mapping can be done, therefore we retain the name Legge-Cut inequality.
Okay. Okay. So any further question or comment? So if not, let's thank Dr. Mo again. Okay. Thank you.